Yeah, good morning and a warm welcome from my side to all join us today, and congrats for joining our webinar about optimizing sample processing for secure cold storage today. Thanks again for joining us. Before we are about to start with our virtual host today is to share some housekeeping notes before. All what I will share to you today and Wilfredo will share to you today will be recorded, and the recordings will be sent out right after the webinar together with a short survey. So no need to write anything down unless you wanted to. So you will receive all the necessary informations and all the details right after the webinar. So don't worry about that one. If you have any questions, don't hesitate to raise them. You have this question button in your participant panel. Please make use of that. Whenever you have any questions, don't hesitate to raise them to us. We are taking care in parallel to the presentation about your questions, and we'll answer your questions anytime during that webinar. Due to some short-term circumstances, Wilfredo cannot join us today in person, but he was able to pre-record at that conference. That is something I want to share with you, but as said, we are there to help you and to answer all of your questions. So I will start right now the pre-recording.
Hello, thank you for joining me today. My name is Wilfredo Marin. I'm a Senior Product Application Specialist at Thermo Fisher Scientific, focusing on biobanking and cryopreservation. Today I'll be presenting Optimizing Sample Processing for Secure Cold Storage. I'd like to welcome everyone to this session. My goals today are hopefully to answer questions using the material in this presentation, and we'll have some time for Q&A at the end of the talk. But I want to encourage some curiosity and obviously keep this momentum for a further discussion at a later time. For now, I can share a little bit more about myself. As I said, I'm a Senior Product Application Specialist at Thermo Fisher Scientific. I've been with the company for almost 3 years now, where I focus on biobanking and cryopreservation within a team that works on controlled temperature technologies. Really, my goals within the company are to help drive collaborations for new technologies and a lot of the workflow solutions, including cold storage and cold chain. My previous experience is in academic laboratories where I work with animal models, as well as particular biomaterial, such as leukemic stem cells, where eventually I was able to manage a pediatric rare disease biobank in Chicago. For today's talk, I'd like to focus on 3 main topics, starting with cryopreservation, how we think of it as a science, what we've learned about what it can do to help or can possibly hurt the cells that we work with. 2, some recommendations and best practices when we're considering creating a custom profile and the intention of some of the steps. And 3, our product solution and what you should be looking for when considering your purchase for a control rate freezer. So let's get started. As you can see, I've called out 2 points in this first section. That's because I will go through a couple background pieces about cryopreservation, as well as summarizing 2 really important peer-reviewed articles that discuss cooling rates and ice formations. I do want to mention in this webinar that it's important when working within the field of cryopreservation that we consider control rate freezers. And the reasoning is fairly simple. We understand cryopreservation as a biological process. We know that if we bring cells down to cryogenic temperatures, if they were normally susceptible to any damage due to enzymatic or chemical activity, that will be halted and they'll be preserved much better. When we use a control rate freezer, it provides an incredibly reliable, traceable, and reproducible set of results. This data can be captured in several forms, but the goal is to ensure precision in cryopreservation and enable better post-thaw outcomes for both the user or the samples that you're working with. Ultimately, in maintaining and capturing this data, you're able to foster collaboration among scientists. We know that we can use the same program across different units, across different sites, And there's a lot more confidence when you can leverage a really programmable method to guide these cells through vital points in the freezing process. I often get asked, well, what exactly are those vital freezing points? Well, I've shared this slide quite often as well to address that, namely because it's a working spectrum of the temperature range that a control rate freezer can function. This is really what it's intended to do. As a sample preparation device, it can bring cells down from the state of human metabolism, which we know is about 37 degrees Celsius. Actually, we've learned just recently that our temperatures may be just a little bit lower than this. But as we move across this graphical thermometer, we expect some events to happen, namely sample nucleation. And it'll occur in a range, usually from -5 to -15, and I can discuss what can actually change that or affect that. But as we move across this thermometer, you'll start to see different thermodynamic events, namely crystallization. And we can consider that as a heterogeneous or a homogeneous arrangement of the ice crystals, all that's happening outside of the cell. We can finish the cell storage by reaching -80. And I often get asked as well, where do certain sample types belong at what temperature? And we can safely say, at least in my experience in a biorepository, we put a lot of our plasma and our sera aliquots in -80 degree freezers. And DNA or RNA can also work in -80. They take up space often, but they can work equally well and be stored long term at temperatures such as -20. In some cases, we were using cells or tissue. We can vitrify them directly into liquid nitrogen, or we can bring down a control rate freezer to these lower temperatures past -137, which is considered the glass transition, and there's T small g. And in pictures that I've seen with kidney livers or other cell types, you can see that when it's vitrified, it looks like a glass. It's not too foggy. You can actually see some of the structure of the organ or the mini organ. So again, these temperatures are very common within cryopreservation as well as long-term cold storage. When it comes to cryopreservation, there really is one hypothesis, one central mantra, and it's quite common. I've shared this slide quite often in several different formats and webinars. But really, the educational portion is to show what is happening to the cell as the temperature is dropping in a control rate freezer or any other cryogenic tank unit. What we're hoping to achieve is large amounts of cell viability and recovery. And so as the temperature is dropping in this big blue arrow, it's also losing water and it's dehydrating. And there's the mantra or this hypothesis is that if you're working too slowly at a cooling rate, which is the degree step down from ambient temperature down that thermometer, if it's slower than 1 degree per minute, you can release a lot of water. It'll actually transport very easily through the membrane and it'll freeze extracellularly. But the potential risk is that you're exposing your cell type far too long in any cryoprotective agent. And in many cases, it could be a DMSO product that can affect some of the analysis later on. And there are some reports that there are some epigenetic alterations when these cells are thawed. And of course, that DMSO also has to be washed out before anything is infused into a patient who could potentially have a reaction to it when they're being treated. On the other end of this is rapid cooling, something that would be faster than 1 degree per minute. And of course, you're getting the same release of water through that membrane. Some of this ice is freezing extracellularly, but because you're moving faster, you're cooling faster, you're really not allowing enough time for it to leave the membrane of the cell. And so this intercellular ice formations probably the most problematic in cell storage because you would not know that these cells are dead or that these crystals have affected any of the organelles or the function of the cell until after you've thawed. And of course, when those numbers are dismal, it's a big disappointment. And so if you can in any way prevent this or work against it or optimize it, that is a big recommendation. And of course, that is the main topic of this presentation. I do like to give examples of certain cooling rates. I think it's important because the audience can work with different types. And namely, when we say 1 degree per minute, it is talking about mammalian cells, and this can be T cells, even CAR T cells, anything that's been manipulated. iPSCs, there's some mesenchymal cells. We have learned recently from a recent poster at the Society of Cryobiology earlier this year that NK cells can tolerate probably a little bit of faster cooling rate, but again, they fall within mammalian cells. And the reason they can do 1 degree per minute is just because of their size and their structure. So you'll see that they're basically within a certain range of size, and NK cells might be a little bit bigger, or bigger cells can tolerate just a little bit faster cooling rates. But particularly the membrane bilayer allows for a lot of that movement of water. We've seen more and more examples of potential organoids or cell aggregates, and that is because they are trying to represent, potentially a mini organ or the minimal units that can represent an organ. And so their structure is obviously a little more complex. They need a little more time for that water to move through several cells. And of course, entirely freezable, but it will take a little bit more time, and you would have to optimize this in a control rate freezer. And you can still use a control rate freezer for red blood cells. I know when I was working with animal models, we would freeze some of the sperm just so that we would have a gene bank of what we were able to manipulate and potentially respawn or recreate. And so I suppose that the natural tendency for red blood cells and plasma is a blast freezer. That's entirely fine. Again, I'll say that the control rate freezer in the larger size units, across all size units, but you'd have more capacity in the larger ones. And the temperature rate or the cooling rate per minute can reach up to 99 degrees, 99.9 degrees. And of course, this will work just well for red blood cells. So just a little bit more background about intercellular ice formations. This is not intended to be any type of scare tactic. They actually do exist. It's something that we don't see often, but until very recently, that's because we weren't able to visualize it. I'm calling out a paper here that's cited at the bottom that really struck me because this is exactly what we warn against, or what we say a product like a control rate freezer can help avoid. In this study, I've just highlighted one of the figures where they were working with a set of cells in DMSO at a 1 degree, 10 degree, and a 50 degree cooling rate. And across these, they had results of over 80% alive within 1 degree per minute, 60% were still alive at 10 degree per minute, and only 20% alive at 50 degree per minute. The reason was because they notice, as you can see this white line through the picture, it's represented in this sort of graph below, where the red will be extracellular ice. You'll have some unfrozen section of DMSO, but then the blocks will highlight any within the cell where there could be a location of ice crystal. And you don't see any in the 1 degree per minute. You see some dark spots here, and they're represented in this block. But now at 50 degrees per minute, far too fast, there are several sections where there are ice crystals inside the cell. Unfortunately, both the 10 and the 50 will be dead when they're thawed. And so, again, we're trying to avoid that with a very optimized control rate freezing step. I will say that in terms of cell health, it was very common that even the 1 degree per minute would have some ice within, even if it's not shown here in the blue. But as you'll see in the next slide, the location of where that ice is very, very important. So this paper, again from a similar group, shows why the location of the ice matters. Here, they were actually working with a certain type of T cells, and I get asked very often as well if we have specific cooling rates for specific types of cells. And again, a lot of that's been optimized in certain labs that are specializing, but I did want to share this. This is Jurkat cells, and this is a DMSO-free cryoprotective agent. And in this top panel, you'll see that they actually created the outline of the cell with an amine solution, and we're able to find where the ice was, and it's on the cell boundary of the cell. So right off to the edge. And basically the key takeaway point is that the intracellular ice crystals are located in sections of the cell membrane that are nearest the extracellular ice. So not necessarily the unfrozen section of the uh, solution cryoprotective agent, but other blocks of ice next to it. And in this particular study, they were looking through several formulations where they were getting their DMSO-free cryoprotective agent. There were with several plots across sucrose alone, glycerol alone, and isoleucine. They were able to determine the best formulation that worked for them and achieve 84% post-thaw recovery. So we know that cooling rate is a key factor in post-thaw recovery, and the composition can also influence the optimum cooling rate. So as a result, influencing the cooling rate requires multi-component solutions, and they were able to determine this during their screening. So with those 8 formulations. Great. So I hope you can appreciate that I've shown you a few examples where the cooling rate really matters. And of course, we determined that a 1 degree per minute is optimal in several cases. And now I'd like to focus and show you where that stems from. So again, another protocol cryopreservation manual where I can highlight exactly what a freezing curve is doing and why it matters. So some things to consider before you're working with cells. Obviously, we talked about DMSO as well as DMSO-free cryoprotective agents. Thermo Fisher Scientific and actually Gibco, which is part of the Thermo Scientific family, offers several permeable or non-permeable cryoprotective agents. This is just a small list of what would be available, but they serve different functions. Of course, those that are permeable, like DMSO, help reduce the freezing point of a solution and cell shrinkage at any given temperature, which creates less intracellular ice formations versus the non-permeable cryoprotective agents, which protect the cell through dehydration. So when there's less water in the cell, obviously there's less potential for ice to form. You have greater osmotic balance. Other things that could affect ice nucleation within a cell, we discuss cryoprotective agents. We know that some of those might be toxic at the higher concentrations when we're doing slow cooling and it's staying at ambient temperatures for far too long. But volume sizes also matter and sample types also matter, as you've seen. We're trying to work against that by giving you 6 preset run profiles and custom profiles in the control rate freezer. So I'll discuss this in the last section where we talk about the product solution. But some other things that are or should be considered are the sample container vessels, such as bags and presses or bags and canisters that allow for easy workflow movement from a control rate freezer into long-term storage. We also have very specific rack types and holders for 2 ml vials or for longer 4 or 5 ml vials. We can work with our customers to create some customized racks for any of the larger diameter type files with larger volumes. And of course, the best way to do this is to design them in such a way where there's enough space for that very simple liquid nitrogen vapor air to flow through the chamber of the unit, touch the surface of all the containers, and create some of that nucleation that we expect. And then when you're designing a profile, or as you'll see in some of the next examples, we want to take that down to our storage temperature. In many cases, it can be a cryogenic tank, or it could be a ULT freezer. And you'll see that the control rate freezer can get down to -80 or -180, which is approaching the temperature of these units. So this is just a nice call out to my colleagues in our consumable side. We do, again, I mentioned we do have racks for both type of vials here. These are the tri-coated screw top tubes from Matrix. I talk about these quite often as a way to minimize pre-analytical variables and help with sample management. Of course, here they're not necessarily in the best type of positioning for proper airflow, but we have seen customers use them in this manner, and again, still achieve some very consistent and reproducible results. So what type of results should you expect? Well, here is a typical cryopreservation freezing profile. I like to show this and again cite some terrific work coming from this group. And again, I think now I think this is the current president of the Society of Cryobiology, and very well deserved, because some terrific work coming from that group, and some of the workshops and the manuals that they're able to provide. I like to consider that what you'd see in the control rate freezer, specifically the Cryomed, represents this panel, and it's an evolution of what you're seeing over here on the right side. Normally, if you were to use any plastic container, something with isopropanol alcohol, you would place the samples, and this is something I did quite often, and put them in a colder upright freezer. And the expectation is that it would freeze 1 degree per minute, and your sample wouldn't react in any way, but this is passive freezing, right? There's no active control of the chamber temperature. More recently, there was a movement, and in some of the IVF fields, we would have access to the vials so that someone could touch them and create that nucleation, and there was manual nucleation, but they would have to do that with every single sample vial, very well timed during this holding step, and so it's very labor intensive and obviously takes time. And here, as you'll see with this latest evolution of freezing profile, you'll have two sections, basically B and B, that represent the cooling profile. And with this automatic seeding step, or I've heard it called in many pharmaceutical cell manufacturing facilities like a ballistic freeze or a cold pulse, it comes down, but it comes back up to meet the sample, and again guides it through those temperatures, those risky potentially ice building temperatures, at the same cooling rate. And then once it reaches something of a safe zone or a stable zone of extracellular and intracellular ice that's not growing, potentially growing, they increase the temperature of the cooling rate. So again, you're saving time and some money with the usage of liquid nitrogen. So I have here just an example, an animation example that I've improved just recently because I've gotten some questions, what you should expect with some of these profiles. So as you'll see, the line, it can move through, and all these steps, including the cooling rate, the automatic seeding pulse, the cooling rate continued, that second triangle block of B, and then your increased cooling rate. Now you've reached an endpoint temperature, again, of your choosing or what's programmed on the preset. It could be a -90 or a -180. What is happening with the sample at the same time? Well, you're moving through those temperatures where you're creating ice nucleation. It's a little release of heat. It's a heat of fusion, latent heat of fusion or crystallization. And then you're guiding it back down because the chamber the temperature environment is able to, the sample is able to track closely with that chamber environment. So one addition that I've done to this slide is mainly to show, because you are reporting this or representing this in the control rate freezer, you're only getting a sense of the one sample that you put the probe in. And you can use different probes. It could be a sort of metal probe that would go in a vial, or you can use a ribbon type sensor. But all around it, the samples, the expectation is that they're doing the same thing. It's a little bit like popcorn. They don't all nucleate at the same time, but they do eventually perform the same sort of thermodynamic process where the water is leaving the cell and at freezing and again stable at long-term temperatures. So this is a follow-up to that. What is actually happening to the cell in those steps? You're getting the water leaving the cell. You're getting some ice formation both inside and outside the cell, and it's better to have extracellular ice. You get that little release of heat. Here you saw the little heat wiggle, but that extracellular ice is actually helping balance more removal of water. And so while the ice at this point isn't necessarily cubic type of ice, it's still building upon itself, and it's still okay to have ice at those edges, right? And now you have your neatly stored cells basically preserved where minimal chance where you're having any enzymatic activity. Great. So now what type of solutions do we offer that work with that can work with you, that you can work to optimize and improve this process? So I will call out the cryomet control rate freezer. And I presented this slide recently at the International Society for Cell and Gene Therapy regional meeting. And I did this with colleagues because we were focusing on GMP compliance. And I can go through each one of these very easily now because, in fact, the cryomet control rate freezer satisfies a lot of these points that such personnel who work in these environments require. As a call out, the materials of construction that we provide with certain documentation and cleaning agents. This would fit in a clean room or clean room adjacent type of environment because it can be sterilized with a vapor hydrogen peroxide type of solution. I think upwards of 35%, which is fairly strong. Of course, there aren't really many seams here where it would encourage growth anyway, and the cryogenic temperatures kind of minimize that exposure. We have data monitoring in the form of a constant real-time sample and probe temperature, as well as having the memory in this unit to store all of the runs for the life of the unit, as well as exporting in this little flap, an optional printer here if you're still so inclined to print or tape in a lab notebook or any type of research journal. Documentation. Well, documentation pertains mainly to, again, the construction of the unit, any type of conformance or compliance. We do have installation qualifications and operation qualifications. Again, all that supporting documentation. It just helps you get started with confidence so that the process that you're optimizing is repeatable across different sites. They all have the same unit. They can do the same thing. And of course, we provide those documents coming straight from the factory where it's built. Again, same point towards reproducibility of the results or the intended freezing, because even though they're different size units, if anything, they would consume just a little bit more liquid nitrogen to sort of fill that space, but the programs are the same on all of them. And of course, the temperature probes are measuring your most representative sample. And that all adds to scalability. You can start with a sort of QC programming with files, and then we see a lot of users grow that with bags, bigger volumes. And again, those accessories still fit in the same unit. And then because we have different size units, you can grow that very, very quickly across different locations. So I do want to zoom in and have a little follow up on what's happening at that UI. This is the biggest difference between the legacy models. What you'll see is it's sort of password protected, so you do require a login. There's different levels of user responsibility, so you can have an admin and sort of a shift worker or an operator type status. There are very easy and intuitive icons off to the left. And of course, because you have this real-time feedback of what's happening inside the chamber, you can get a graph and scroll through some of the data information or some of the step information or any potential alarms or alerts on this screen once you've started the run. And of course, if you're just running the same program over and over, you can utilize run last. And this is a warm-up mode so that you can finish your process and then get started quickly on the next one by warming it up. But this is typically what you'll see, and of course you've seen this is one of our programs, and obviously it closely matches what that latest evolution of a freezing profile looks like. And then you would see the sample with the red dots being the different sample steps and how closely it's staying and tracking with that chamber temperature. Again, this meets 21 CFR Part 11 requirements, which is a requirement in itself in a lot of GMP settings, cell manufacturing settings. All that means is that it's password protected and the electronic records will stay there for the life of the unit. Both runs and any type of events for potential audits when you need to know who did what and when they did it, so that you can either do it again or avoid it. And of course, we use some of those same files whenever we're helping optimize with our users, or there's some troubleshooting steps when we're trying to find any type of settings that were changed inadvertently. So great, this sort of summarizes what the control rate freezer in this new look and new user interface can do. Obviously with the look of the new sort of gray stainless steel, easy to clean. There are some remote alarm contacts. There's a Wi-Fi availability in certain regions. I believe EU is one of them. And we do have an optional printer that sits just right up top. This Wi-Fi connectivity would be sort of a complement with the UI. You'd probably want to stick with the UI because of the capabilities to save and store all the runs and easily program and customize a profile. But then the Wi-Fi you could use if you have other instruments, basically for remote monitoring of the unit, the status, what step it's on, and again, any of those same alarms would appear on a Wi-Fi. Touchscreen, as I mentioned, 21 CFR Part 11. That export, very easy. It's not automated, so you still manually have to find. You would basically go into the icons, find the reports, and export as many as you'd like on an encrypted device. But anything that comes from it, the PDF is obviously the user responsibility to maintain safe. The PDF run report would be one that is non-editable. So that's the one that a lot of our users basically sign off on and put in their final reports. And again, that the unit is very simple. It just uses liquid nitrogen, a low pressure supply of 22 psi, maybe 20 or plus or minus 30%. That's really the only requirement is power, LN2, and then just space for some of the venting as the air is pushing through and sort of recirculating. The performance is incredible. It's still matched with the legacy unit, but the feedback because of this UI allows for more capture, more regular intervals of feedback. And again, parsing of the data, partitioning it, and then securing and encrypting it and storing it on the unit itself. And in some cases, obviously we offer 3 different capacities, but in some cases, at least in North America, we do offer a FDA class 2 or general purpose model. So definitely that's something to consider if you think that you're working with cells that require that designation. So this was another slide that I shared in that ISCT meeting. namely because specifications are important, but of course, as you can tell from some of the cryopreservation background and some of those accessories and freezing profile evolution, specifications do not tell you the entire story. I think they can really point you in the right direction. We know that, for instance, this temperature range, when we're working down that temperature gradient, not a lot of control rate freezers can actually reach negative 180 for an extended amount of time. That's something we're very proud that we're able to do because, again, that's the temperature of a cryogenic storage tank. Um, you have dimensions internally, externally of the unit so that you know, and we can obviously provide these as well as a technical data document, but just the opening of the door, um, how much space you would require. So we have some internal dimensions of this chamber and external dimensions, and then of course all the accompanying accessories that you could do, whether it's bags and presses or bags and canisters or vials. And in many ways, you can actually combine the 17 liter accessories and the 34 liters into this 48 liter chamber unit. So one quick thing I didn't mention is that if you're still inclined to use our free software for PC interface, and this would be remote control of the unit, we still have that connection on the back. It's an RS-232, and it would go to a USB adapter. So you would still be able to basically create a profile on a PC and run it from a PC if that's what you were used to doing. Again, we're sort of encouraging the UI being the main use, and complementing that with the Wi-Fi because of those two capabilities and the compliance to 21 CFR. And of course, there's a terrific warranty on this because, again, we're confident that the unit is going to be well supported for several years to come. And again, part of this presentation is a little bit of awareness because we know that a lot of users are very comfortable and confident using a legacy model of the control rate freezer. But of course, with similar performance, a little bit improved because of the data capture, but also just user experience with the UI. We can see that some of those 10-year-old units that are out there, control rate freezers specifically, this is a really good opportunity to take advantage of any particular type of trade-ins or trade-ups. There is a lot of great support for this. If you have additional questions, we have videos that I believe are now posted on YouTube. So three great ones. One would be a box to bench, a preventative maintenance, and then I contributed to one discussing the different connectivity options. So Wi-Fi as well as that RS-232. And then a third one that I'll sort of allude to in these next couple slides. But definitely make sure you check out those short videos, maybe 5-6 minutes. And if possible, look for the Kaon 3D Tour app. So this is a snapshot of that where you can actually see an example of one of the racks inside. You can open, close the door, zoom in on some of the UI features. But again, there's some hotspots here where if you click on them, you'll get a little description and maybe see if there's something that opens or closes. This here is a sample probe connection, so you can see maybe how to switch those out. If you're using bags, you'd like to use a ribbon type probe, or if you're using vials, one with a sort of metal tube sleeve that would go inside. And then we have some smart notes that discuss certain applications, and this is a call out to preparing samples for long-term cryogenic storage, which again helps support the topic of this presentation. Lastly, because cryopreservation does not stop once you've reached cryogenic temperatures, I've included this slide to show what other things Thermo Fisher offers. Again, we have the same type of flexibility and scalability of our units. Almost everything you'll find here comes in various sizes. Of course, this is a CryoPlus floor model with a large opening here for accessibility of your racks and samples. It's an automatic fill, so it could be used in liquid settings or vapor phase. The stainless steel units are almost all exclusively vapor phase, but they're much larger capacities. They're a little bit taller, so require more room. And then As we see, when you're freezing down bags or samples, we'd like to either do short-term storage with a liquid dewar or one of the potential transport or IATA type approved dewars where you can ship these to a collaborator with small subsets of samples. And of course, this is an example of that LN2 supply. Oh, and here we see what that Arctic one would look like in a shell case so that it's protected from any jostling, any tilting or vibrations. Lastly, I'm just going to highlight to this quick slide, and of course I didn't discuss any of these other instruments, but I did discuss the cryomed as it pertains to the T-cell therapy workflow. And this slide actually came from a virtual workshop presentation that I gave maybe a couple weeks ago with other colleagues of mine. But the main point is that if you're going through all of these steps for optimization of your cell, of your potential product, you don't want to have the cryopreservation step be basically the most disappointing one because we aren't able to control, optimize, and document our control rate freezing. So a lot of these customers are working in closed automated workflow systems. We can piece them together and they could work they can work together. And of course, they all offer the same call outs that I've done for all of our LN2 products. But now, as I mentioned, one of the connectivity options is the what's called OPC UA. And I won't go into detail, but I think it's a great topic for another discussion. When you're working with a control or a distributed control system like Delta V, you'd be able to connect a cryomed control rate freezer and actually control and produce reports of your own and time-stamped event logs so that not just a cryomed, but additional instruments that are part of this cell therapy manufacturing would provide some contextual data. And this is all sort of predictive analysis, and it helps make better business decisions overall. This is my last slide just to show now we offer the CTS Cellmation software. You'd likely be hearing a lot about it coming soon, how it supports these different types of instruments, and of course the cryomed being one of them. I think our module is actually one of the first ones that's out, so definitely feel free to reach out if you're interested in cryomed and this is something that you might have IT infrastructure to support or looking forward when growing or scaling your business. Definitely consider this Cellmation software from Gibco CTS. The Thermo Fisher Scientific mission. I think this is something that really appealed to me when I first joined. I take plenty of pride in the work that I've done over my career. And of course, to come to this company where we're continually doing great things with diversity and different business resource groups. I mean, it's an incredible opportunity. And of course, we're only as good as we are because we leave it up to the customer. We enable you to make the world healthier, cleaner, and safer. Thank you so much for having me today. I was really happy to discuss cryopreservation, a little bit of background, what we're doing to provide some solutions that help optimize your process. I hope you've enjoyed the talk.
Yeah, thanks, Wilfredo, for taking us through that journey. I'm just looking, because that is the time for your questions. I received already a couple of questions, or we received a couple of questions, which for the most, we have an answer. If there is any additional question, just write your question in the question area. And aside that, I want to ask my colleagues from Thermo, is there any question on your end? Which you received?
Right, so if there are no questions coming in on chat, I will mention some of the questions that we have received, right? So
Yeah.
the first one is, what type of liquid nitrogen supply tank does the cryomed work with? So the cryomed actually requires a low pressure supply tank of 1.5 bar This is specified on the product brochure, and know that we do provide these tanks. So feel free to reach out to us for the tanks as well.
Thanks, Swati. I'm just checking again. I'm sure they come in the day-to-day work, right? So, but just to be sure that we answered on any questions. Yes, that seems to be the case, that all questions are answered with the exception of one, and we will reach out to that participant after the webinar. So thanks
Definitely.
also to Thermo. Yeah, sorry.
No, definitely. We'll get back to the question
yeah.
that we couldn't answer on chat. But I will mention another question that we did get, right? Do you offer customizable solutions for accessories, right? So, you know, can we customize any accessories for the cryomet? So we obviously have a range of accessories, racks, and so on. All of these are specified on the brochure. But should you have a special consumable that you're working with, and you don't think there is a rack that matches the dimensions of that consumable, know that that is something we are willing to look into and check on a case basis. So definitely check with us if you have a specific requirement as far as your accessories are concerned, and building those custom racks. So we're quite flexible.
Okay, and that is a perfect bridge, Swati, for me to share with the audience that we share the recordings, as said before in my intro. I'm happy to answer additional questions whenever they might appear. You will receive that mail, and to that mail, webinar@avantrosciences.com, you can raise your questions. So don't hesitate to, even after the webinar, don't hesitate to ask us any further help and any further application, as Swati said as well. So thanks for joining us today. And I wish you, and we wish you, a great rest of the day, as long as it's sunny. Currently in Germany, it's raining, but in some other areas in the world, there is sun shining, I'm sure. So thanks again, and happy rest of the day, and goodbye.